Welcome to Ask and Learn.
In this problem, we have a cylinder which initially contains nitrogen gas at a specified state. The gas is compressed polytropically until the volume is reduced by a half. We want to calculate the work done and the heat transfer in this process. We assume that this cylinder is stationary and thus the kinetic and potential energy changes are zero. N2 is an ideal gas with constant specific heats. The thermal energy stored in the cylinder itself is negligible, and the compression or expansion process is quasi-equilibrium. The properties of nitrogen at an average temperature of 350 Kelvin is R, its gas constant, which is 0.2968 kilopascal meter cube per kg Kelvin. Its specific heat at this temperature is 0.744 kilojoule per kg Kelvin. Now, for our closed system, which is the contents of the cylinder, there is no mass transfer, so we can write the energy balance equation as E in minus E out is equal to the change in energy of the system, delta E. So the net energy transfer by heat, work, mass, etc., which is the left-hand side of this equation, we have the boundary work into the system, since the gas is compressed, minus the heat lost, which is out of the system, Q out. And this is equal to a change in internal energy of the system, delta U. Now, delta U is equal to M into U2 minus U1. So on a unit mass basis, we pull out the mass of the nitrogen. So we can write this WB minus Q as M CV, the specific heat at constant volume, times the temperature change T2 minus T1. So that's our energy balance equation. Now, we need values to substitute into this equation. So we'll first find the final pressure and hence the final temperature of the nitrogen. And we'll use the relation that P2 V2 to the power 1.3, remember this is a polytropic process, is equal to P1 V1 to the power 1.3. And we can rearrange this equation and find the final pressure P2, and P2 is equal to the volume of the initial state over the volume of the final state, all to the power 1.3 times the initial pressure P1. So for a volume that is doubled or a volume that is halved, V1 over V2 is 2. So the initial volume is twice the final volume, and this is to the power 1.3 times the initial pressure, which is that of 1 atmosphere, 100 kilopascals. We get the final pressure P2 to be 246.2 kilopascals. Now we can use the other relation that P1 V1 over T1 must equal to P2 V2 over T2. Now that we have the pressure, we can calculate the final volume. So if we rearrange this equation, we see that the final temperature T2 is equal to P2 V2 over P1 V1 times initial temperature T1. So this is equal to 246.2, which is P2 over P1, 100 kilopascals, times V2 over V1 is a half, that's 0.5, times T1, which is 298 Kelvin. Hence, we get the final temperature of the system to be 366.9 Kelvin. Now we need to find the boundary work into the system. So the boundary work into the system is equal to minus the integral from state 1 to 2 of PdV. So this is the PdV work. And for a polytropic process, this is minus P2 V2 minus P1 V1 all over 1 minus N. And this is equal to minus MR, and we can write this in terms of the difference in temperatures, MR into T2 minus T1 all over 1 minus N. So we expanded the numerator and made it MRT. So now we can substitute our values in here. So the mass of nitrogen is 2.2 kg times the gas constant we said was 0.2968 kilojoule per kg Kelvin. And the change in temperature T2 minus T1 is 366.9 minus 298 Kelvin. This is all divided by 1 minus N, which is 1 minus 1.3. And so we get the boundary work into the system to be 149.9 kilojoules. So now we have the final temperature of the system as well as the boundary work done. So we can actually calculate the heat transfer. So the heat that leaves the system, Q out, is equal to, from our energy balance equation above, the boundary work into the system minus mCV into T2 minus T1. And we'll put in our values here. So this is 149.9 kilojoules. We suppress the units since everything's in SI units, minus 2.2 kgs for the mass times the specific heat for nitrogen at this temperature, 0.744 kilojoule per kg Kelvin, times the change in temperature of 366.9 minus 298 Kelvin. Hence we get the heat transfer out of the system to be 37.2 kilojoules.